section 2A. Where's Izzy? Hold on a second. Izzy, are you here?
Yes, sir.
Okay, I missed you somehow. I can see it. There you are. Okay. So we're working on 2A derivatives of function, and we're really on this. We're doing this group of questions right now. And once we've done that, we'll work on the other stuff. But essentially, we're going to find the derivative. So we're using this notation f dash of x. And the derivative is basically a function that tells you the slope of the tangent line at any given point x. And you start with the function y equals f of x. And we're going to use what's called the power rule. So let's jump right into that and do some practice. So first one I'm going to do is going to be question 9, or at least a version of question 9. So here is the function. Pretty nice looking function. It's 9.5 t squared plus 5t. And we are going to find its derivative. And if you remember yesterday, the power rule is the one we're going to use, which says you multiply the thing by the power and then you reduce the power by 1. So 2 times that guy gets you 19, and now you've got a t. Can anybody remember the shortcut for what the derivative of 5t is? What's the derivative of 5t?
Just 5.
Just 5. Yeah, not too difficult. This one doesn't have a number, but see if this one had a plus 7, wouldn't the derivative of any number, including plus 7, be 0? So you wouldn't write anything down. Now, they ask you a couple of questions which we haven't talked about. So let's do it now. And that's the domain. So it's been a while since you've done domain. Can you remember 141? The domain is the usable values of the variable. So in this case, the usable values of t. Now, 9.5 t squared plus 5t. You can evaluate that function for any value of t that you like. And so the domain, when it's everyone, using interval notation, is that. Are you comfortable with that answer? That the derivative of this function is everyone. What is the derivative of 19t plus 5? What are the usable values for that function? Any suggestions? Don't overthink it. It's actually pretty obvious.
All of them again?
All of them again. So those extra little bits tagged on at the end you might not say, well, I wonder why they're asking us about it. They're really just emphasizing the fact that we are dealing with functions, and domains. Knowing the domain of a function is a very useful thing to do. So here's my next question. I'm doing an X one. Right, if you want to do the derivative of this polynomial, you multiply by the power, you reduce the power by 1. You multiply by the power, reduce the power by 1. The shortcut for negative 5x is negative 5, and the shortcut for the number 1 is you get 0. So there's your derivative. Pretty straightforward. Yeah. They're going to ask you for its domain. So the domain of f of x and the domain of f dash of x. And, oh, well, here goes. Isn't the domain of every polynomial in the universe all the numbers? if you are a polynomial is just a fancy name for the function contains various positive powers of x's, right? Like x cubes and x squared and so on. That's a polynomial. The domain of every polynomial is that. And have you noticed that when you differentiate a function that's a polynomial, isn't the derivative just a slightly smaller polynomial? So won't the answer be those guys? So can you see that you might be repeating yourself quite a few times when they ask you for the domain of the function and the domain of its derivative? Because if the function they're talking about is a polynomial, aren't the answers going to be these two guys every time? So don't read any more into it than that. I want to find another example of one of their questions. So if you hold on a second, that was one I just made up. See if I can find the way they phrase them. Let's see. Here we go. What's that doing? Oh. Will you put down your attendance right now? Because there's something weird going on that I just want to fix right now. Because if I don't, I'll forget that I didn't fix it. Then I fixed it. So you just put your attendance down right now. It means you don't need it at the end. Rabbi Sign was doing something weird with one of the questions, and I wanted to fix it because I probably would have forgotten. So let me try that again. This time it should work. Right, let's show you some of these questions. So, where are you? Okay, make it a little bit bigger. There, well, I'll come back to the one. Right, there's the question 9, or at least the version they've now got. Type in the function here. If you want to do a domain, essentially you would do bracket, negative. Can anybody remember where the infinity is stored?
I think
Where do you get infinity?
You can type it.
You can? What?
Yeah.
I've never tried that before. Oh, you mean? Oh,
I
that
can
is
also type
cool.
union.
What? You can type in union?
Yeah.
Oh, okay. So see the things you learn. Cool. Right. If you go into symbols, there's infinity if you're kind of lazy. Right. So that's what it would be. And if you know that one answer is the same as another one, can't you save like 2 seconds by copying and pasting? So no biggie. Polynomial, derivative. Very easy polynomial, derivative. Do you see they want the domain and range? Isn't that domain going to be this guy? Isn't that domain going to be this guy? And I haven't even done the derivative yet, have I? But don't I know if you differentiate a polynomial using the power rule, won't I just get a smaller polynomial? And polynomials, domains, and ranges are also infinity to minus infinity. Now, here is a function, and we've defined its derivative. And according to the power rule, you multiply by the power, 4, and then you reduce the power by 1, so it's 4x cubed. And then you go plus 4x. So far, so good. Okay, out of that. Now, what you see here are 4 functions. One of them is the original function, That's this guy. And the other one is the derivative. And they've put them on the same picture. So the blue one is the original and the red one is its derivative. And we are meant to figure out which one of these four pictures is the right one. And do you know how we're going to do that, don't you? We're going to use Desmos. So let me kick into Desmos. And I think I'm going to have to go out and in to make that happen. Right, you should be looking at Desmos right now. Yes? Okay, so you go y equals x to the 4 let's try that again, x to the 4 plus 4x. And then your second function is going to be y equals 4x cubed. And nobody noticed my mistake. It should be plus 4. Right. Now, the color scheme's wrong, but we can make that change. I can make that one blue. And if you click on your mouse, oops, there we go. If you keep your finger on the mouse, you can change it to red. So if you're one of those people that wants to see the thing, right, there we go. I don't like the window. It's kind of vertical and not very horizontal. And I'm going to change that by just making this window -5 and that window 5. There. And maybe move it up, shrink it back a touch. There we go. And that guy will be one of these guys, which you can't see, of course. Right. So one of these fellas here, I guess I could shrink him up. There. So it's this one, this one, this one, or this one. If I move this window down, I shouldn't do that. Looks to me like it's going to be that one. And you got your answer. Any questions so far? So if I gave you a polynomial, would you feel comfortable about finding its derivative, f dash of x? And if you were being asked its domain and range, you better say, yep, that's going to be dead easy, because as long as it's a polynomial that I'm dealing with, won't that be the domain of the original, and won't this be the domain of the derivative? Because that's what you get when you have polynomials. And if you had to do a sketch of both, are you comfortable that you know how to do Desmos and tweak it a little bit so it looks more like the choices? If we are good at that, can I move on? Or do you want to see some more examples? We good, guys? Good. Okay. So let's chalk that off my to-do list. Now, I know it's slightly out of sync, but that's okay. Let's do this thing. Identifying the values of x where the derivative function does not exist. So we're not going to be giving you a derivative to calculate. These questions are just going to give you a sketch of a function. Y equals f of x. And if you look at that function, let's assume that this function continues forever. If I said to you, where does this function have a problem if you're trying to find the slope of a tangent line? It's another way of asking yourself that question. For what value of x then does this function have a problem trying to get a tangent line? And don't overthink it. It is kind of obvious, I think.
At 3.
At 3. So the function is not differentiable. Now let's look at some of the other things that are maybe a little bit less obvious. And I'm going to make them all at 3 because I want to. Would you agree that trying to find the slope of the tangent line to a function where there's a vertical asymptote is a bad idea? Would you agree you cannot find tangent lines when there's a vertical asymptote happening? Does that seem reasonable? So jump discontinuities are problems. Well, some of you might be saying, well, I could find a tangent line there, and I can find a tangent line there. So what's the problem? The problem is that that slope might be 3 and this slope might be -1/2. Don't you need a single number to be a tangent line? You can't have 2 tangent lines. And no, you're not allowed to pick the one that's got the dot in it because it happens to have the dot in it. That's not allowed either, right? So just to emphasize why that's not good. Here's one that's less obvious. This function is not differentiable at 3. You just got a funny little, like, top of a house kind of thing, you know, the little thinking on, a little corner. Corners are problems. If I said to you, what is the slope of the tangent line? You might say that it's a vertical line. Right? Great. It could be vertical. Problem with that is vertical lines have a slope of infinity. Right? And infinity is not a good number. It's not a number at all. So those guys fail. That funny little corner thing, you know, the ones that look like that, they're called cusps. So if a function has a cusp, it's not differentiable at the places where the cusp, or if you like the word corner, where the corners are, right? They are bad ideas. What's wrong with this function at 3? Why can't you differentiate this guy at 3? There is no corner, right? It's a smooth curve, yet you cannot differentiate it at 3. What's the problem? Okay. What would be the slope of the tangent line if you drew it at 3? At that point where my finger is. There. Right? And isn't infinite a bad idea for a derivative? Right? You're not allowed to be infinite. You have to be a number or you're not differentiable. Right? So in this case, you're looking at a vertical part of the curve. So if you look at a vertical asymptote, isn't it a little bit clearer why you can't have a derivative? It's a little bit less obvious that you can't have one here, but it's kind of the same reason. If this did happen, wouldn't the derivative have to be vertical? And here, wouldn't the derivative have to be something that's vertical? Just one more. What's the problem with this function at x equals 3? Because it's not differentiable. What's the problem at 3?
Their cusp.
Yeah, well, we don't call that. You could call it a cusp, but you shouldn't. A cusp is actually is for is more when that happens. When that happens, although it looks very similar, that's basically a corner. Right, but it's for the same reason that a cusp doesn't work. Cusp tends to be when the shape meets like this, and a corner is more when it meets like that. I guess it's being pernickety, but you know, it is what it is. And I just almost forgot a baby one. I guess it's one of the easiest ones to miss, and that's probably why I missed it.
So is it a problem with it like drastically changing directions?
Yes, that's the reason that that causes problems. Drastically changing direction in both of these. Slightly different looking, drastically changing directions, but enough to make a difference. That's why these don't work. That's a removable discontinuity. Why is that not differentiable at 3? Why can't you find the derivative of this function at 3?
Because it's undefined at 3.
That's it. If your function doesn't have a value, there's nowhere for the tangent line to touch the curve, because there ain't a curve where it wants to touch. Even although you can tell where it should be, that's still not good enough. So here is a kind of a family of things that will screw up your derivative, right? These are the places where a derivative can't be found, right? So we say the function is not differentiable. Now it's very visual, which I like, because I like visual things. I'm now going to show you some examples in the homework. And you should be looking at a graph. Are you looking at a graph, guys? Okay, I wish I could make it bigger. So I'm going to see if I can tweak something here and make it bigger. Although that probably means there. Can you still see the graph, or will I have to go out and in? Can you see the graph?
Yep, you still.
Okay,
I
we
still
can.
see it.
All right, if you see it, I'm sure everyone can, right? Make it a little bit bigger. Maybe that's too big, but whatever. All right, here we go. Down in this box, we are going to put the x coordinates. Well, I'm not going to type them, I'm just going to ask. And you are going to tell me the x coordinate of places where this function is not differentiable. And I can see 3. So give me any one of the 3 that is no good. Actually, I might write it down now. Give me the x coordinate of some place where this function is not differentiable.
2.
Don't know why it does that. Just because I'm changing the size, it goes and changes the whole blinking sausage. Right, 2 is a good one, because that's maybe the one you would have missed. If you look really carefully at 2, isn't it vertical at that point? Is it coming down? So 2. Another value of x.
Oh, obviously -4.
Right, that's a cusp. And one more.
0.
And isn't that a jump discontinuity, right? All jump discontinuities are not differentiable, right? All removable discontinuities are not differentiable. All vertical asymptotes are not differentiable, right? Guess I could make this even bigger. Oh, this time it decided to behave. I can only see 2 this time. If you see a third one, tell me, but I can't see any more than 2. Right, so tell me the 2 places where this function is not differentiable.
-1.
I agree.
And 2.
And 2. And if we were going to put names on them, wouldn't that be a removable discontinuity? And wouldn't this one be a cusp? Right? Cusps look like to me, cusps look like the top of houses. That's kind of how I imagine them. Go away. I won't tell you how many I see this time, but give me the x coordinate of a place where this function is not differentiable.
Is it vertical enough at 5 to be 1?
That's the sneaky one, yes. I am assuming that at 5 or darn close to 5 isn't the curve vertical. You see, that's bad news. That one's an easy one to miss. The other one's obvious, I think. What's the other x value where this function is not differentiable?
One.
Agreed. Are you comfortable now that if you were given the shape of a function, that you would be able to say the places, the x coordinates where there's a problem, right? Okay, and this is the last one of the batch. I'm going to give you 10 seconds just to have a quick look at it. And then I'll start asking. And this will be the last one of this type. Okay, there are 3 places where this function is not differentiable. 3 values of x.
-2.
1 and 3.
I have a -2. And at -2, would you agree it's a corner? Those are cusps, everything else is a corner. I heard 1, and that's what I jump discontinuity, and I believe 3 was the other answer, and isn't that another corner? Okay, I think that went well. Are we good? Do we need to do any more graphing ones, or you feel if someone gave you a sketch, you could tell me where a function's not differentiable? Okay, then we are on to our last thing that we need to do in that section, last topic. So cross that off my little list. Now we're going to look at how to make a simple sketch of what the derivative function looks like when all you're given is a sketch of the original function. Let me show you, as best I can, how you do that. Green. Just wondering what colors I'm going to use. Right. Suppose you're being asked to do a very simple sketch of this function. And by that I mean a sketch of its derivative. Right. So you're told f of x. It's a polynomial. How do we actually do a simple sketch of its derivative? Let me show you how you would tackle that question. Well, I would try and draw something like the original, or at least have a good imagination and think of what it would look like. And the first thing you do is you find places where the derivative would be horizontal or not existing. In this case, would you agree that at that point there, the derivative would be a horizontal line, which is 0, and at x equals 3, it would be horizontal. So far, so good. Now, for those values of x, in this case at x equals 1, draw imaginary, very faint dotted lines that you could rub out at the end if you want to. And at this point here, the derivative is 0, so you put a dot. And at this point here, the derivative is 0, you put another dot. Because what you've essentially done here is you've broken the original thing into 3 pieces. I'll call this region 1, everybody over here. I'll call this region 2, everybody from here to here. And this one is going to be my third region. And so I've got region 1, I've got region 2, I've got region 3. If you pick any point of this curve in region 1, do you notice that if you drew its tangent line, this pen would be its tangent line. Do you notice that the slope is always pointing upwards? So doesn't that mean that the derivative function is a positive number? You agree? And positive numbers, this is going to be where the derivative function is going to go, means that the curve lives above the x-axis, right? That's where positive numbers are. Now, what's the derivative going to look like in region 2? Well, if you pick any point in this region, isn't the function going to have a downwards pointing derivative? And downwards pointing means negative. So that means the derivative lives below the x-axis in region 2. Will it be positive and live above the x-axis, or will it be negative and it lives below the x-axis in region 3? What shall I be doing in region 3? Shading above, positive, the x?
Positive.
Yes. We agree, everyone here? Right. So increasing, positive, decreasing, negative, increasing, positive. Now, once you've done that, you're pretty close to being finished. Because what you want is a curve that starts here, passes through the x-axis at 1, gets into here, passes through the x-axis at 3, and finishes there. And you pick the smoothest, simplest curve that does all those things. And we've now just drawn the derivative function. Does that make sense? Now, yeah, we've got time, good. Taking me a little bit longer to do this one because I want to be a little bit more accurate than I typically would be. Does anybody recognize that curve? What if I
Sine
just
curve?
say again?
Is that the sine curve?
It is. So my original function here is the sine curve. Of course, it, as you know, it goes on forever, but I'm only going to do that little snapshot of it. And then I'm going to use the technique that I used here. So it takes a little bit of a while to do the setups. Hopefully you can hang in there. are some of the key values. Now, in this function here, would you agree that there is a horizontal tangent at a half pi? Would you agree that the tangent line is horizontal? So I'm going to drop this guy down here like that. And that's going to be at a half pi. And isn't there also a horizontal tangent line at 3/2 pi? And this guy here, I guess we should put his value in, is 5/2 pi. And there's one more here, 5/2 pi. And that means that we now have 1, 2, 3, and I'll count that as a region, 4. In region 1, positive or negative? So if you did a tangent line to the curve here, would it be positive pointing up or negative pointing down? So what do I get in region 1?
Positive.
Correct. In region 2? The rest of you are allowed to answer.
Negative.
Agreed. Would you agree the next one is positive and then the next one is negative? Isn't it go up, down kind of thing, right? At this point here, isn't the derivative 0? At this point here, the derivative is 0. And this point here, the derivative is 0. And now I'm going to try, not a most artistic person in the world, but there we go. That's what the derivative function looks like. Does anyone recognize that guy? This one is the sine function. Do you recognize the red one?
Cosine.
Is that an amazing surprise to you? That the derivative of sine x is actually the cosine of x? Maybe it's kind of, yeah, that's what I would have expected. But I don't know, to me that seems quite unusual, but kind of nice. Because doesn't that mean that I now know what the derivative of sine x is? It's cosine x. Let's, for the next one, do some shapes that have problems with them. Here's my function, f of x. Let's say that guy is at 3. This guy is at 5. Let's make that guy at 8. You know, that could be 10. That could be -1, you know, and so on. Now we're going to try and create a sketch of what the derivative of this function would look like. Now we're getting into things that involve a lot more thought. But I'm going to do at least the beginning, just like I did before. I'm going to find the places where I know for sure the derivatives are horizontal lines, right? And I'm going to go and drop this guy down here. And that means at x equals 3, the derivative is 0. And at x equals 8, the derivative is 0. So I know that. I'm going to add one more special point. And the special point I'm going to pick is any place where the function is not differentiable. And in this case, it's 5. Okay. And I'm not going to put a dot there because the derivative at 5 is not 0, right? It's 0 at 3, it's 0 x equals 8. But at 5, there's just something happening, right? So it's just a separation, right? And these dotted lines really don't exist. Once you've got, once you've done this picture, all that shading isn't really there, right? These vertical lines aren't really there. Isn't the only thing that's left is the curve, right? So these are just constructions, right? Things that you put in to help you construct the graph. But if you put them in nice and faint, or you do them in pencil, you could really just rub them out when you're finished, right? And nobody cares. So that means that this shape is broken into regions 1, region 2, region 3, and in this case, region 4. Right, that's a little bit better. So I've got region 1, region 2, region 3, and region 4. And we're going to do that shading thing, right? In region 1, is the derivative positive or negative? Region 1.
Positive.
Okay, so I'm going to shade here. Region 2, positive or negative?
Negative.
Region 3.
Positive.
Finally, region 4.
Negative.
Yes. Now, there's a very, very, very likely mistake you're going to do here. Because of what happened here in the previous times, you're going to say, I got this. You're going to go like this. You see what I'm trying to do with my finger? I don't want to write it because if I've got it in pen, I can't make it go away. But you're going to make it go through here, reach here, cross the x-axis at 5, reach here, curve round, cross at 8 and head back home, right? Kind of what we did here, but that's not correct. I'm now going to show you what the real curve looks like. Now, is that what you thought it was going to look like? Well, let's try and explain why. Would you agree at x equals 5, the derivative is not 0? It just doesn't exist. If you're in region 2, is it the last guy that you get to is roughly where my finger is? And isn't that a slope that's like negative somebody? So do you see why the last dot is down here at negative somebody? When you get to this one, would you agree that this endpoint here isn't it upwards? Isn't it a positive number? So at the join, right, at the place where there's a break, here, right, at the jump discontinuity, isn't there going to be a jump from a negative derivative up to a positive, right? You're going to change totally the way you go, right? And to emphasize that, you see how this has caused a jump discontinuity in the derivative. Now you might think, well, why is this straight? Well, I guess it could be curved a little bit as well, but all I'm doing is making sure that it goes through the origin from here to here, and it goes through the x-axis from here to here, and through the x-axis from here to here. Does that make sense? Why this would be the shape for the derivative when you have a jump discontinuity? Because a sudden change, as someone said, good way of phrasing it, with a sudden change in derivative, shouldn't there be a sudden change here? Now, there is variations on jump discontinuities, and you have to be aware of them. Can you imagine a jump discontinuity where at this point here and that point there, the the slopes could be equal, right? Imagine a straight line, you broke it and then made it go down. If you were looking at what the derivative would look like at this point here, it would be negative because it's pointing downwards, so it would be down here somewhere, right? And it would actually have that shape. You see, it would be a removable discontinuity because the derivative at either side was the same slope. It just doesn't have a derivative at that point, which we know it doesn't. And so you have a removable. So what does that tell me? Jump discontinuities in the original will cause either jump discontinuities in the derivative, or in a very, very rare case, it might cause a removable discontinuity. But they're always going to be a problem at 5, right? Either the problem is going to be a pretty major one, like the derivative has a jump discontinuity, or it might be that it still has a problem, but it's a removable discontinuity. And that is us. So if you didn't catch what I said last time, last name for attendance. If you've already done that, then you are good to go. Bye-bye, and I will see you tomorrow.
Right, thank you. Bye.
Bye.
Thank you.